Alexis wants number 9, Syra? 9 and 10. Okay. Here we go. Number 9, a .144 kilogram baseball is pitched horizontally at 38 meters per second. The batter hits a horizontal line drive at negative 38 meters per second. What is the ball's change in momentum? So the ball is coming off the bat at exactly the same speed that it went into the bat, but the direction has changed. So you're looking at change in momentum. We could draw it out. The ball is going that way at 38 meters per second. It makes contact with the bat and then rebounds at negative 38 meters per second. So the way the question's worded, they've already given you which direction they want to call positive and negative. So change in momentum is just momentum final minus momentum initial, which is just mass times velocity final minus mass times velocity initial. So then the mass is 0.144, and the final velocity is negative 38 minus 0.144, and the initial velocity in this case is positive. So you've got a negative value here minus something positive. I mean, if you work that out, that should be negative 11. Does the setup make sense? Number 10, you have a physics dragster. It's traveling 35 kilometers per hour east when it hits the gas and accelerates at 12.5 meters per second squared for 3.25 seconds. What is its change in momentum during this time? So change in momentum is momentum final minus momentum initial, which is mass times velocity final minus mass times velocity initial. There's a lot we need to tweak here. Hey, man. So the 35 kilometers per hour, we're going to have to divide that by 3.6 to turn that into meters per second. So what is that? 8 something? 9 something? 9.7 meters per second. And we're told that it hits the gas and accelerates at 12.5 meters per second squared for 3.25 seconds. So we need to find VF. So we have to do some kinematics here before we can start doing momentum. We know that VI is 9.7. We know the acceleration is 12.5. We know that it accelerates for 3.25 seconds. So we want to find the final velocity there. So we're going to use VF equals VI plus AT. So that's going to be 0.7 plus 12.5 times 3.25. That's 50.33 meters per second. So then the change in momentum is going to be the 1205 times that 50.33 minus 1205 times 9.7. So I could make these numbers, no, I shouldn't do that, never mind. I could. I mean, we could make these numbers a little bit, like we could ballpark it, like you didn't have a calculator. I would ballpark this by saying, this is effectively 1200 times 50 minus 1200 times 10. So you're looking at 12 times 5 is 60, 2 zeros from that one and a 0 from that one is 60,000 minus 11,000. No, 12,000. You're looking at 48,000-ish, which is close enough to that answer. But this is the method. You need to use the kinematics to get you your final velocity. That final velocity becomes final velocity for your momentum. Okay. There was another way to tackle these kinds of questions, unless someone else has any questions. Yeah. Okay, you've got a 5 kilogram object being dropped. So VI equals 0, and then the thing starts to fall. VI equals 0, acceleration equals negative 9.8, because it's being dropped. They tell you it's being dropped from a height of 2.5 meters. And you want the object's momentum after 0.25 seconds. Now, you don't know how far it's fallen after 0.25 seconds, so you don't actually, like this piece of information here isn't super useful. What you do know, though, is that because it's dropped, the VI is 0, and it's falling due to gravity, so it's negative 9.8. Actually, let's make it positive 9.8 and call it down negative, or down positive. We need VF, and we're going to use time to get it. So after a quarter of a second, I mean, assuming this thing hasn't hit the ground, you use kinematics to find VF, and then momentum is mv. Assuming that d is less than 2.5, which it should be. Is that enough? Because if you think back to the lab we did, I had you drop from no less than 2 meters, and all of you had data for over a second. So a quarter of a second after something's been dropped from 2.5 meters, it hasn't hit the ground yet. You've done that lab. So you just need to find out VF. Anybody else? You know, is that enough? Okay, then we're gonna look at a concept called impulse today. We've already kind of danced around this a little bit, but I'm gonna formalize it here. The definition of impulse. Now, when you think of impulse, what do you think of? What does that word mean to you? If you have an impulse to do something, for example. Yeah. Like conceptually or metaphysically? Yeah. Like not literally, Liam's not literally pushing you, but Liam may have suggested that the pizza in the cafeteria tastes really good today. And so now all of a sudden you desire the pizza. Now you go get the pizza. Something made you do something. You were pushed to action. This word impulse in physics is conceptually the same. Now, if Liam, rather than telling you about the quality of the pizza, Diego, Liam actually walked up behind you and just shoved you, that's functionally the same thing. But in this case, you haven't been, metaphysically moved towards the pizza. You've been literally shoved forward. What about you has changed when Liam literally shoves you forward? Your position's changed over a particular time, sure. Now you're moving. You could be moving. I mean, think about the context of the question in the chapter that we're in. If he comes up behind you while you're walking forward and pushes you from behind, now you're moving forward faster. Your momentum's changed. Or if you're walking at Liam and Liam's having a particularly bad day and he's like, I'm not moving for Diego. Shove. You had a forward momentum. Now you have a backwards momentum. Your momentum has changed. So when we're looking at moving, like changing how an object is moving, impulse, this word impulse really is just the push. And you think about what a push is just a force applied for a given period of time, right? If I push you for a long time versus just a little shove, the rate that, or the amount of momentum that is changing is going to be different, right? So we've talked about it a little bit already. The idea that if I flip, but you don't flip back, I will flip back. We've talked about it a little bit already when I first introduced momentum. I said that, well, momentum is mass times velocity. We think about how things are, how heavy they are, or how massive they are, and how fast they're moving. I gave this to you in kilogram meters per second. I then made this kind of hand wavy argument up top here by looking at the units that said, well, I could just multiply by seconds here. And sorry, I could take my units of force and multiply by seconds and get the exact same units I had before. So that momentum must also be related to this idea of a force times a time. And so I told you that the units could be newtons per second. And then we never used that again. We did P equals mv for all that's the rest of that lesson. But I did tell you that momentum was equal to a force times time. Whether you remember it or not, we haven't used it yet. Those words left my lips. That is the definition of impulse. So it's not just, so impulse in its simplest is a change in momentum. But things don't just spontaneously change their momentum. If you're not moving now, you have no momentum. And a little while later, now you're moving, something had to happen in between. Someone shoved you. You got up and walked. Something happened to cause your momentums to change, and that is what we call impulse, the push. We can derive this concept of the change in momentum from Newton's second law. We said, if you think back to Newton's second law, F net equals ma. That's Newton's second law. And back in kinematics, I gave you a definition for acceleration. Back in kinematics, we said that acceleration is equal to a change in velocity divided by time. Well, if I take this definition for acceleration and I shove it into Newton's second law, what I'm going to get is that your net force is just going to be equal to your mass times a change in velocity divided by a time. If I multiply both sides by time, these times are going to cancel, and we're going to get m delta v, which is a change in momentum, is going to equal a net force times the time. And what time? The time the force is acting. And so what we get here is this. We get that F net times time is going to equal your mass times your change in velocity. This whole thing, both sides of this equation, reference a change in momentum. So this is the impulse equation. We looked at this side of the impulse equation on Friday. I just had you guys start calculating how momentums changed as things acted. But now bringing this idea in here too, we can look in a different way, we can approach the same kind of thing. How are momentums changing in a bunch of different examples? So conceptually, this isn't overly difficult. Let's apply this now to a bunch of different situations. Here we go. So, during a particularly intense game of Smash Brothers, Luigi, now for those of you who have never played Smash Brothers, the hammer in Smash Bros is a particularly devastating piece of equipment that you can pick up during the game. Assuming, I don't know where that number came from, but assuming the mass of the hammer is 9 kilograms, Luigi swings it at Mario's head at 16 meters per second. Luckily, somehow Mario's mustache brings it to a stop in a quarter of a second. Things don't stop instantly. Things take time to stop, which brings about a whole bunch of really interesting analysis kinds of questions. I saw that, well, I'll pause here for a second. Talking about how facial hair impacts how things stop, a bearded boxer is less likely to get concussed than a beardless boxer, because the hair actually has a measurable effect on the quality of the punch that strikes a bearded boxer versus a beardless boxer. The hair on your face, those of you who have hair on your face, makes it less painful when you get hit there. Here, you're nodding like you're like, yeah, it does. I regularly get hit in the face and it hurts less. Have you experienced this? You were nodding with way too much like I've been there. Okay, maybe I don't want to know. Okay, I'll take you at your word. Okay. I mean, conceptually, it makes sense, right? Like, it's a little bit of cushion there. I mean, I just trimmed my beard back. My beard isn't going to be super cushiony. But if you look at Yendel, when Yendel grows his out in November, there's a lot of hair there. Like, if you can think about how that would be difficult if you, for whatever reason, you wanted to punch him in the chin, that could be hard to do. So Mario's mustache manages to bring this hammer to a stop. What is the force exerted on the mustache? I mean, the force exerted on the mustache is going to be the same as, it's going to be equal to the force exerted by the mustache and it's going to be equal to an opposite. And if this was the information I gave you, and we hadn't talked about the impulse equation, the way that you guys would have to solve this problem based on the stuff that we looked at before was, okay, well, the net force is going to be F net equals ma. I need the acceleration. Well, I know I've got a hammer moving at 16 meters per second. It takes this much time to stop. Stopping means Vf is 0. I can use kinematics to find the acceleration. I take my acceleration, I plug it into F net. Before today, that's how you'd have to solve that problem. But now, having introduced to us the concept of momentum and looking at impulse, we don't have to do any of that anymore. We have enough information in the problem and the impulse equation to solve this. So let's look at it. We're going to say that the net force times the time that it acts is going to be equal to your mass times your changing velocity. Well, the mass of the object that's having its velocity changed times by that change in velocity. So F net's what we're looking for. So F net times the time it takes to bring that hammer to a stop is 1/4 of a second. So 0.25. So I'm going to have F net times 0.25 is going to equal 9, the mass of the hammer, times the change in velocity. Now, the change in the velocity, the final velocity is 0. If you recall, delta V is V final minus V initial. So my delta V is going to be my final velocity is 0 minus my initial velocity of 16. So F net is just going to equal the mass of the hammer times negative 16 divided by 0.25. That number is going to be negative 580. Nothing stops in an instant. Everything takes time. And so if you looked at, for a second, what is going on in this equation, what happens if we were to somehow increase the time it took to bring the thing to a stop? What would that do to the force? It would decrease it. If somehow you could start the stopping process earlier, the net force on Mario, in this case, would decrease, which is interesting. We have also, and that's really, and it's going to be some of the stuff that here where you look here on the bottom, this idea here that if you increase the stopping time, you decrease the net force applied, is really the concept behind so much safety equipment. Bare knuckle boxing is not a thing anymore. We have gloves now. Bare knuckle boxing used to be a thing. I mean, and it is a thing in some dark corners of weird alleys and pubs I don't visit.
There's a full thing. They're not completely.
Well, I mean, the closest thing we have to legit bare knuckle boxing would be like MMA, like, or UFC, like bare knuckle like actual I mean, it's wildly dangerous. Yeah, so there's a little bit of padding there. Because any amount of padding is going to increase this time value here. If you punched someone in the head, just your fist, this time would be very small. But with the glove, or any amount of padding, the glove starts to absorb and starts to slow you down before the fist actually gets to the face. This time increase, this force goes down. That's why amateur boxers, they even have another step further. Like when I had my graduation, we had a high school I went to, all the grads every year went on there's a retreat weekend. It took all 200 or 220 of us and to a camp up past Chilliwack, and we were all there. Grade 12 teachers and all these students. And the guys decided it would be fun to, after all the teachers had gone to bed, bring all of our mattresses into one large room, set up a boxing ring, and two guys brought gloves and helmets. The helmets are absolutely necessary because none of us had any idea what we were doing. And the helmet just functions as another padding to prevent you from getting a concussion. The more layers you add, the force is going to decrease, which is wildly useful. Let's do a couple more examples. A soccer player kicks a 0.450 kilogram ball at 25 meters per second. If the goalie stops the ball by exerting this much force, how long does it take the ball to stop? Now, this in the real world, this is really hard to measure. But there is equipment that would do this. If you wanted to test this, there are pads that exist, and the pads, they're little stickers. You stick them to things, and they are designed to explode at different levels of force. So you take your goalie gloves, you cover them with these stickers, maybe it's 5, 10, 15, 20, maybe in the force range that you're expecting. You stick these stickers to the glove, goalie catches the ball, you see which ones have exploded and which ones have not exploded. You have an idea of how much force is required. You could hook the goalie up to, I mean, a lot harder to do, but you could hook the goalie up to some accelerometers and calculate it that way too. This is hard to do. But let's say you're able to do it. How long does the stop have to be? Believe it or not, finding this or measuring this, 215 newtons, is going to be way easier than measuring the amount of time it takes to catch a soccer ball, which you'll see here momentarily. So we've got a 450 gram soccer ball, or a 0.45 kilogram ball, moving at 25 meters per second off a soccer player. The goalie's going to catch it, exerting this much force. How long does the thing take to stop? If you don't have the impulse equation, F net equals ma, you're going to find A, you're going to plug it into kinematics. But with the impulse equation now, we have a way to relate force, time, mass, and a change in velocity. So F net times time equals m delta v. You need to be on the lookout for these, especially on a final exam where I perhaps don't tell you what concepts you need to use to solve a problem. You can save yourself a lot of work if you remember this equation and look for the things, the pieces that lead you to it. So we've got a net force. Net force is 215. The time to stop is what we're looking for. The mass of the ball is 0.45. And the change in velocity, that delta v, is always v final minus v initial. The ball is stopping. So that's going to be 0 minus, well, initially the thing's moving at 25 meters per second. I'm hoping someone can see that I've made a mistake in here. I'm modeling something I see from students all the time. What have I done that's going to be weird here in a second? Granavin, I saw your hand first. No, we want that in meters per second. We want the mass in kilograms, and we want 25 in meters per second. That needs to be there. I made a different mistake here today. Well, the ball does start at 0, but what am I measuring? I'm measuring the goalie stopping it. Anybody else want to take a stab at where I've made my mistake? I'm trying to model a particular error. Maybe it would help if I drew the problem. So here's gloves. are really bad gloves. How many fingers does someone have? 4 fingers. There's hands. There's a ball. Really big ball, really small hands. Boom, 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 boom. The ball is moving in. The velocity is, at this stage, 25 meters per second. The ball is going to reach the person. The velocity is going to come to 0. What haven't I done in this problem yet? We said that it was 25 meters per second. Positive. Which implies what? No, the final velocity is 0 because it's being caught. Yeah, if I calculate this the way it is, the time's going to be negative. Does that make sense? No. So if I look at my picture the way I've drawn it, by saying that the initial velocity was 25 meters per second, that is dictating that to the right is positive. When you go to stop the ball, soccer players, which way do you have to exert the force? Sorry? You're pushing against, yeah. So in this particular example, to the left is the direction the force is going to be applied. Well, we said to the right was negative. So that way is the direction that the force is being applied. This direction just happens to be what? Negative. So what do I have to do to this equation to make this make sense conceptually? No, I want to leave 25 and 0 the way they are, because 0 is the final velocity, 25 is the initial velocity. Here, Day? That value needs to be negative. Because you're exerting a force back against the direction the ball's coming in at you at. You got to be really deliberate with your minus signs. Now we go ahead and we solve this thing. We're going to divide both sides by negative 215. And you're going to see here, that's going to cancel. The time is going to be 0.052 seconds. 5/100ths of a second. Not a lot of time to bring that ball to a stop. Quicker than any of you could measure with a stopwatch. Let's change the question. I want to change the next part. If the goalie is required to stop a 6.5 kilogram bowling ball traveling at the same velocity. So I don't know how it's getting at that velocity. Maybe it's in a cannon. You shoot the bowling ball at the soccer goalie. We're going to change these two things. We're going to say that we want the goalie to stop it in the same amount of time. How much force would be required? So we're going from a 450 gram bowling ball to a 450 gram soccer ball to a 6.5 kilogram bowling ball. The force required to stop that thing, what would it be? We want the same amount of time. Well, the impulse equation is going to look like this. The net force times the time equals the mass times the changing velocity. The mass is now 6.5. The changing velocity is still the same, 0 minus 25. We want the same amount of time, 0.052 seconds. What force is our goalie going to have to exert to make that happen? Someone with a calculator, what value do you get? Try that again. That's 0.052. I got a different value. 6.5 times negative 25 divided by 0.052. That's the value I got. That is an impressive amount of force. The goalie's going to break his wrists at the very least. So the impulse equation is actually wildly useful. Let's take a look at a couple more, 5 more, and we'll call it. A student jumps off a desk. When they land, they bend their knees. So for those, you guys have, I'm hoping that you've lived a life. You've run around, you've played, you've gotten into trouble, you've climbed trees, you've jumped off things. There is technique to jumping off things. That's the technique. Vian, wake up. Vian, how do you jump off things? Yeah, how do you jump off things? Oh, you have not lived. Jump off something. Jump off something small. Here's a chair. On the chair. If I were to just step forward and lock my knees, you already have a pretty good idea that would be a horrendous. I'm not going to demonstrate that because you have an understanding that on one hand that would be wildly painful. On the other hand, at my age, almost 40, I could seriously screw up my knees. And with a 4-year-old and a 2-year-old, well, seriously screwing up my knees would be a really bad thing to do. But you have this intuition, right? You know it hurts. You step, you lock your knees, this is bad. So when we fall, like you cushion yourself, you catch yourself a little bit. Why? By doing this, by giving myself some leeway, what have I done?
Well, it's you don't put pressure on the ankle, so they can when you can just at the point where you grab the ankle.
I mean, there's still a force on my ankles, but what like?
I mean, it reduces it.
It reduces it, but why? Because I still haven't stopped yet. There's a whole portion of me that's catching the rest of myself, right? Like all the muscles in my legs are catching my torso. I'm increasing the amount of time it takes me to come to a stop. And when you do that, and again, I've said it a bunch already, when you increase anything you can do to increase the amount of time it takes you to stop, you're decreasing the force on you. I mean, so we can extrapolate this even a step further. There are techniques for falling effectively from all sorts of different heights. I mean, I jumped off a chair. It's what, 2 feet off the ground? I caught myself with my knees. I'm good. I over-exaggerated it a little bit, but I did it. Has anyone jumped off a building? Even a 1-story building, a 15-foot roof. There are techniques for this. Perhaps you've seen it in movies. What do people do when they jump off a height like that? Yeah, they roll. Like it's not just catching yourself with your knees, because even that's going to do some damage. You catch yourself with your knees and you kind of roll yourself forward. You roll it all out. Because all that whole action, you're still moving. The time it takes you to come to a stop is much, much longer than just like locking your knees and here we go, I'm going to hit the ground, this is going to be awesome. Right? You're increasing that amount of time. So we can actually play with some of the math here. Why does this help prevent some serious damage to the knees? Here's why. So let's take a student. Let's say your average student weighs 65 kilos. How much time does it take to stop, do you think? Like I jumped off the chair there. How much time did it take me to stop? And it's not the how much time did it take me to fall. It was the stopping only started when I hit the ground. So stopping only starts here. Like when you hear me hit the ground, my stopping has begun. Just weird to think. And it only lasts till I get to here. So what is that? Quarter second maybe? Maybe even that's a little short. Maybe it's a half a second. Let's call it a half a second. So the time to stop is a half a second. What's the force required to bring me to a stop? Well, or this person to a stop. F net times time equals m delta v. How fast was this person? How fast was I moving? Let's say it was me. Let's change this. Now leave the mass 65. That's wishful thinking. How long did it take me to come to a stop? Well, my final velocity. Here we go. Let's do this. We're looking for F net. The time it took me to stop was maybe, let's say it was a half a second. 65 kilograms. I do not have 65 kilograms. I have more than that, but that's okay. Let's roll with it. VF, or V final, equals V final minus V initial. The final velocity for my jump was 0. Sorry, for my landing, final velocity was 0. What was the initial velocity for my landing? The initial velocity for my landing is the same as the final velocity for my falling, right? So what's the final velocity for my falling? How far did I fall? I fell 0.42 meters. I fell under the acceleration due to gravity, 9.8 meters per second squared. The initial velocity for my fall was 0. Let's find the final velocity of my fall so that I can find the initial velocity of my stopping. So VF squared equals VI squared plus 2AD. VF is going to equal the square root of 2 times 9.8 times 0.42. I hit the ground moving at 2 times 9.8 times, 2 times 9.8 times 0.42, square root of that answer. I was only moving at 2.87 meters per second. So that final velocity for the fall becomes the initial velocity for my stop. So that's going to be 2.87. And we're going to find that the force upwards on me from the ground was, actually, 65 times negative 2.87 divided by 0.5 seconds. And we get that the force upwards on me was 373.1 newtons. That is the force required to bring me to a stop, the net force required to bring me to a stop. What if I locked my knees? Locking my knees brings this down to almost 0, not quite 0. But let's say it brings it down to, I don't know, a tenth of a second, 0.1. The only thing that would change is this value here, it goes to 0.1. So this would be if this goes from a half a second to a tenth of a second by locking my knees, this negative 373 Newton force, so the force exerted upwards on me by the ground, becomes that value. 1,866 newtons. Something as simple as bending your knees reduces this force by a significant margin. A couple more examples. Coaches for many sports such as baseball, tennis, golf, basketball, for those of you who play basketball, can often be heard telling athletes to follow through either with their swing or with their shot. Why? Yeah. Not necessarily. Why is follow through so important? So they don't what? But what? But why? But why is that important? Do I have any golfers in here? Okay. Yeah.
I mean, like, if you put a ball, and the ball basically hits back, and you stop, wouldn't the ball hit back harder?
Not necessarily. I'm going to throw down the impulse equation here. F net times time equals m delta v. Let's assume that in all these cases, the force with which you're hitting the ball remains constant. What does follow through get you to do? So for those of you who are uncertain about this term follow through is, bat to ball, I swing, I don't hold my swing back at all, the swing goes all the way through the ball, comes out the other side, and the ball's now ideally moving that way. Nope. Because the direction is determined by the angle of impact, not the follow through. What does a follow through do? Ideally, in a perfect world, ball coming in leaves the bat going the other way. If the ball is leaving your bat going the other way, or your tennis racket going the other way, or your golf club going the other way, if your bat, your club, your racket travels as hard as you can make it travel in the direction you want your ball to go, it's going to be in contact with that object longer. Does that conceptually make sense? Effectively, what you're doing is you're using that implement to catch whatever you've got and fling it in the opposite direction. If you can do that, this increases time of contact, and that's what delta t is in the impulse equation. Delta t is time of contact, or the time you apply your force. In every sport you play where there's any level of contact, if you follow through, this increases. If this remains if the force remains constant, the time increases, and the mass is also constant, because you're not changing the mass of the ball. That would be weird. You hit the baseball and it becomes heavier. That'd be weird. If the time's increasing and these two are constant, what's that going to do to your delta V? It's going to be bigger. It's going to be increasing as well. This increases. Sorry, that guy increases. Now, I don't necessarily know. I mean, in all the sports that I played, I never once had a coach explain to me, this is why you do this. Never good. You just do this. It makes things go better. Well, why? This is why. The academic will tell you there's a concrete reason why follow through is so important. Increasing the time of contact increases the velocity the thing's going to leave. The physics is relatively simple. Okay. Here's another example, same idea. Conventional wisdom suggests that cars should be made tough and rigid to prevent injury during the collision. They used to be. Cars made in the 60s and 70s into the 80s were basically hard metal shells. New vehicles are built with large crumple zones. Why? Yeah, Lena. That's all it is. If you have two rigid objects, they come together, they're done. They stop immediately. By designing a vehicle with a crumple zone, the collision starts and then goes on for a while. It's not going to be pretty. Your car is almost certainly going to be totaled. In the conventional wisdom with a tough and rigid car, your car is going to probably be fine. It's the contents of the car that are going to suffer as a result of having a rigid car. Contents of the car are usually people. If you decrease the time a person stops, you're not made of tough, rigid material. You're soft and spongy. You pay for it. So by increasing the crumple zones, time to stop increases, net force decreases. Conceptually, wildly powerful. The car's fine. Why did everybody inside the car die? Said people in the 60s and 70s and 80s. Now, that car looks absolutely trashed. How did the people inside walk away? It's counterintuitive. But you walk away, if someone's got to take the force. If the car takes the force, the occupants don't. If the car doesn't take the force, the occupants have to. It's counterintuitive, but it's wildly powerful. Another one. Using the principle of impulse, let's talk about why airbags are a thing. Did any of you experience an airbag exploding in your face? None of you? Airbags are really cool. You guys are all aware of how airbags work, yes? Okay. There was an airbag recall a couple years ago. Inside your steering wheel, where the airbags are, before I go further, do any of you drive with your feet on the dash? Is that a thing people do these days? Yeah, don't do that. So, or like, even if you drive like with your arm across the steering wheel, the reason they tell you to put your hands at 10 and 2 is, yeah, control's an important thing. But if you put your hands at 10 and 2, the airbag goes off between your hands. If you put your hands like you're steering weird, or you're like hanging your hand out the window and you're at 11 o'clock or 12 o'clock, airbag goes off, your fist goes into your face or your neck or your chest or wherever the face ends up relative to the angle the thing was at, right? It's because inside your steering wheel, there is a shaped explosive charge. That explosive charge is designed to, when a car feels like it's reached a particular level of impact, that charge goes off, immediately inflating the bag in a teeny, like fractions of 1/100ths of a second. Almost no time, that thing is fully inflated and in your face. Before your face can reach the area of space occupied by the bag. And then as soon as the thing's inflated, there is no more force inflating the thing. Now it's just this soft cushion that you then lean into. Unless your hand was in front of it, now you're punching yourself in the face really hard. Or if your feet are up on the dash and the airbag goes off, now your feet are getting bent back up at you really hard. All that does, the airbag exists. Everything is F net times time equals M delta V. The airbag increases this. Decreasing this. Because this doesn't change. The mass of your face is the mass of your face. The velocity your face was traveling at is the velocity you were traveling at, and you are going to stop. This whole side is constant. Increasing time means the net force goes down. And every safety piece of equipment in your car is designed for this. Crumple zones, seat belts, airbags, all of it is designed to increase the amount of time it takes your body to come to a nice, relatively comfortable stop. Decreasing the force on you. Flip the page. I got one more. The TI class supertanker is the largest, at the time that I made this booklet, it was the largest ship in the world. A couple years ago. When fully loaded, this tanker has a mass of 509,000 tons. And if you recall, a ton is 1,000 kilos. So we're looking at a ship with a mass of 509 million kilograms. And it can cruise. We don't use knots. Well, we're not going to use knots in class. We're going to say that this thing at top speed is cruising at 31 kilometers per hour, which we're going to convert right away to 8.61 repeating meters per second. Ships are capable of performing an emergency stop. They call it a crash stop. And what they do is they use the end, they throw the thing in reverse. Don't do this to your car. It's wildly damaging to your transmission. Ships are designed to do this. The propellers will go full speed backwards. It puts immense strain on the thing, but it will do this. The engines on this ship are massive. They generate something like 5.22 times 10 to the 6 newtons of stopping force. That is 5 million. The force, that is 5,220,000 newtons of force. How long does it take to stop the ship? Now this 31 kilometers per hour, you'll notice, is school speed zone type speeds. You would think not very fast. You've all driven at this speed. Hopefully this is what you do on your way here as you drive past Godson. Not overly quick, but now you're not a car. You weigh 509 million kilograms. How long does it take to stop the thing? Impulse equation. F net times the time equals your mass times the changing of your velocity. We don't have to use dynamics and kinematics anymore. We can use impulse. So the net force is acting against the ship. So it's going to enter this impulse equation as a negative value. Negative 5,220,000 newtons times the time is going to equal your 509 million 6 kilograms. Your final velocity is 0. Your initial velocity was 8.61 repeating meters per second. How much time does it take to bring that ship to a stop? Punch in your calculator, what do you get? What'd you get? 839. Sorry? So then you divided that by 60. If you decide that this ship needs to stop, it's going to take you 14 minutes to do it from full speed. Just because of a little bit of math. That's wild to think about. I think anyway. Last period on a Monday, you might be too tired to be blown away by that, but that's wild. Okay, I'm done. Here you go. All of it. Go play. And tomorrow we'll look at collisions and explosions. Apply the impulse equation to a bunch of different scenarios. The answers are there at the bottom. I believe in you. You can do it. Let me know if you have any questions.